Welcome back. This is part 2 of the chapter 15 flip. We pick up with 15.3, which is talking about chemical hazards. So many chemical hazards can be harmful to us, cause cancer. Lots of these are going to be carcinogens and teratogens and things along those lines. Uh, but sometimes we have, there's a broad array, is kind of what I'm trying to get at. So a toxin is something that could be dangerous. So a toxic chemical is going to be something that causes temporary or permanent harm or death. Here are a couple of examples. There's definitely some overlap here. Carcinogens, mutagens, and teratogens. Carcinogens, of course, are going to cause cancer. There are many things that cause cancer. You are probably familiar with a lot of those. Mutagens are going to be things that cause mutations. Many of those are also going to be carcinogens if the mutation happens in the right place. And a teratogen is something that specifically harms embryos and fetuses, or it could be a mutation, like a mutagen that impacts the gametes before they become an embryo. Um, they're heritable, basically heritable carcinogens, if that makes any sense at all. Some teratogens are um, things that, like my wife, when she was pregnant, she was only supposed to eat a certain amount of fish per week because there are mercury is an example of a teratogen. It disproportionately affects a fetus. So that'd be kind of an example of a teratogen. Long-term exposure can mess with our systems in major ways. Our immune system can be compromised due to things like radiation. That would be a immune disruptor. Uh, Neurotoxins are going to be things that harm our nervous system that can cause all sorts of issues here. And you've probably heard of several of those as well. But again, we're typically talking about something, a chemical that causes our systems to change in some way. The endocrine system can be disrupted in major ways. That's where BPA is going to roll in. So we'll talk specifically about BPA and the way that it is affecting human systems, specifically males. Um, but it does so through mimicking hormones. Some pesticides do the same kinds of things. They become hormone mimics or hormone blockers. BPA, again, is an example of that. So, again, we'll cover that in class pretty thoroughly. But essentially, the idea is BPA mimics testosterone. So, males that are exposed to BPA don't produce as much testosterone. And we'll talk more about that later. Steroids are another example of something that disrupts our hormone system. So, what can we do? You can limit your exposure to hormone disruptors. Avoid processed, prepackaged, canned foods. Eat certified organic produce because those hormone disruptors can't be used in those types of products. Canned foods can be troublesome because BPA lines the inside of many canned goods, so like soups and things along those lines. Glass and ceramic cookware, again, because sometimes BPA is used in plastics. Sometimes it's used in like an aluminum pan. It'll be used as a liner on an aluminum cookie sheet, something along those lines. So basically, you're just trying to avoid things that are that affect or that are used, that BPA is used in the production of them. Sorry about stumbling through that. Many baby bottles and the water bottles that we carry around, many of those are BPA free. So when you buy a reusable water bottle, you just want to make sure that it says BPA free. Again, we're trying to limit our risk. So 15.4 picks up how can we evaluate our risks? Well, there's a way to put a number to it, and that's toxicity. We're measuring how dangerous something is. There's an old expression that the dose makes the poison. The dose is the level of the chemical that has been ingested. So, um, something like ibuprofen can relieve pain and can help with headaches and some of those types of things. But if you take enough of it, you can overdose on ibuprofen. And occasionally, those overdoses can lead to really extreme effects like death. I lost a former football player at one point to an overdose of ibuprofen. So The dose makes the poison. And that's true of all toxins. A little bit of some things is dangerous, but a lot of anything is dangerous. Sort of along the lines of you might have heard the expression everything in moderation with respect to your diet. Like sugar isn't bad in small doses. Things like carbonated drinks aren't bad in small doses, but if you drink a case of Mountain Dew a day, that's not a great thing because you're taking in too much. Your dose is too high. Same is true of any medicine. So other things other than the dose are going to be things like age. Young children are way more susceptible for a couple of reasons. Number one, they take in more air than I do. My son breathes a lot faster than I do because his lungs are smaller. He drinks more water than I do because he needs to take more in because he can't hold as much. So he takes a little bit in and then pees it out and then takes more in and pees it out. My bladder is bigger. I can hold more water, so I don't have to drink quite as much as he does. Um, Also, your genetic makeup, something like poison ivy, there's a chemical in poison ivy that I'm very allergic to. My wife is not allergic to it. So for her to have a reaction to poison ivy, she has to have a crazy high dose of it. If I'm within 10 feet of it, I have a rash the next day. So my genetic makeup makes me predisposed to be vulnerable to that chemical hazard. So there are a lot of things that can determine how poisonous something is, and there are a lot of variables. Kind of continuing that, solubility is going to affect how dangerous something is. If it can get into your cells, then it's worse. Persistence is another thing that's really bad. It's another I don't know, vocab word, I guess. PCBs we've talked about with biomagnification. DDT is really persistent. It's a chemical that we've studied in class that is used to control malaria and kill mosquitoes. And big surprise, it's good at killing mosquitoes. It's also pretty good at killing people. So if something is persistent, that means it sticks around in the body, it sticks around in the environment. Once it's here, it's here. If something isn't persistent, it's not as dangerous because it gets pumped into the air and it gets broken down. Not a big deal. I talked a little bit about biomagnification. We've covered this already in ecology, so just don't forget that when things like PCBs that are fat soluble especially, they can amplify as they move up the food chain. So that causes lots of dangerous things. I've talked about my roommate in college that got mercury poisoning from eating canned tuna. That was a short-term effect. He stopped eating canned tuna and he recovered. Can cause birth defects in developing or in pregnant moms. I talked about that with the biomagnification stuff again when we studied ecology. So something that we're going to spend a little bit of time with is this dose response curve, and let me just jump to the graph. So this is our dose response curve. So showing the dose along the x, the percent of the population killed by a given dose is here. So at a low dose, nobody's killed. At a really high dose of whatever this is, everybody's killed. This mark right here is really important. The LD50 is going to be a number that I'm going to ask you to calculate, and I'm going to ask you to estimate based on the dose response curves, because that's where it's the lethal dose for 50% of the population. So you go up the y-axis, you find 50, you come over and you drop down. So our hypothetical dose is 7. So we can use the LD50 to estimate how much pollution is allowed, if that makes sense. We can set our acceptable limits based on our LD50. We know, okay, if this is going to kill 50% of the population, we need to have nowhere near this amount released in nature. EPA uses these kinds of things to set our pollutant levels and think about our water quality reports and all that kind of fun stuff. Some chemicals are really dangerous in low dose. Some you have to get a ton. Like you can drown or you can overdose on water, but that would be a lot of water. Most chemicals are of course going to fall somewhere in between there. So how do we estimate how dangerous something is? How do we come up with LD50 data? A lot of it is animal testing, and that of course has many ethical drawbacks. We use case reports from doctors. If someone goes to the doctor and has mercury poisoning, it gets reported. So then we can collect population data, and we can say, okay, so this person had this level of exposure and they didn't die, or this person did die from this level of exposure, and we can kind of work backwards and forensically come up with that LD50. We can also do epidemiological studies where we compare people that are exposed versus people that are not exposed. So you might see those commercials about mesothelioma on TV all the time. That was an epidemiological study that resulted in a lot of lawsuits and things along those lines. But we can't always do that. Often we don't have a great experimental group, and often the dose isn't high enough to create an LD50 curve. If it's going to kill 50% of the population, well, what's the difference in the phenotype between dead at 50%, dead at 100%? It takes a long time, and often we get these combined effects between many chemicals that you're exposed to just throughout your daily life, whether you work in a risky profession or not. So, and these really can't be done on new hazards because no one has been exposed to them. So I'm going to leave off here with the second video. I'll finish. We've got just a few slides left that we'll go through in video 3.